Welcome to What If, the show that explores the absurd, the impossible, and the purely hypothetical with the help of real science. I'm your host, David, and joining me as he does every week is our resident physicist and master of the theoretical, Dr. Richard Sterling. Richard, welcome back to the show.
It's a pleasure to be here, David. I'm always excited for the topics we tackle.
Well, today we have a topic that sounds like it's been ripped straight from a blockbuster disaster movie, but it's actually rooted in some truly fascinating cutting-edge physics. The question we're asking is, what if a microscopic primordial black hole passed straight through the Earth?
Yes, it's a scenario that pushes the boundaries of our understanding of matter, gravity, and planetary science. The answers, or at least the theoretical answers my models have been generating, well, quite astonishing.
Astonishing is exactly what our listeners come for. So let's start at the beginning. I think when most people hear the term black hole, they picture a giant cosmic vacuum cleaner out in space swallowing stars. What is a primordial black hole and how is it different?
Right, and that's a fair picture for stellar mass or supermassive black holes. Those are the cosmic giants formed from the gravitational collapse of incredibly massive stars at the end of their lives.
Okay, the classic type.
Primordial black holes, on the other hand, are entirely hypothetical. The theory, first proposed by Stephen Hawking and Bernard Carr, suggests they weren't formed from stars at all, but from the extreme violent density fluctuations of matter in the very first moments after the Big Bang.
The very first moments. So you're saying these things could be almost as old as a universe itself?
Precisely. Relics from the dawn of time. And because they weren't born from the constraints of stellar evolution, their sizes could vary dramatically. Some could be massive, but many are theorized to be incredibly small, microscopic even.
Now, that's the part that's hard to wrap your head around. When you say microscopic, what kind of scale are we actually talking about? Is it like a grain of sand or a dust mote?
Much smaller. The models I've been running, which align with the prevailing theories, focus on a primordial black hole with the mass of, say, a large mountain or a decent-sized asteroid.
The mass of a mountain, okay.
But that entire mass is compressed by gravity into a region smaller than a single proton, smaller than an atom's nucleus.
Wait a second, hang on. You're saying the mass of Mount Everest or more is crammed into a space smaller than an atom? How is that even possible?
That's the nature of a singularity. The density is almost incomprehensible by human standards, and that is precisely where the danger lies. The threat from such an object isn't its physical size. Its size is irrelevant. It's about its mass, and the gravitational havoc that much mass concentrated into a single point can wreak on its surroundings.
So we have this mountain mass, atom-sized bullet hurtling through space. Let's set the scene. What happens at the moment of impact with Earth? Would we even see it coming?
Almost certainly not. It would likely be moving at a significant fraction of the speed of light, and it's far too small and dark to detect with any current telescope technology. The first indication of its arrival would be its arrival.
Wow, no warning at all.
It would punch through our atmosphere in less than a 10,000th of a second. As it does, it would be moving faster than the light traveling through that medium, creating a flash of Cherenkov radiation, a brief, impossibly bright streak of blue light in the sky. But it would be over before any human eye could possibly register what it was.
A blue flash? And then it hits the ground? What happens then? Does it just make a crater?
This is where my recent modeling has produced some truly unbelievable findings, David. Previous theories assumed it might pass through relatively cleanly, a sort of neat puncture wound. But the simulation shows that the immense tidal forces and the subsequent energy deposition are far more violent than we previously imagined.
Tidal forces? You mean like the moon and the oceans?
Precisely the same principle, but on a mind-bogglingly extreme scale. The gravitational gradient across something as small as an atom is so steep that the side of a rock nucleus closer to the black hole would be pulled with monumentally more force than the far side.
So it's ripping atoms apart?
Exactly. This process, famously known as spaghettification, would instantly ionize and vaporize a cylindrical path of rock as it enters the crust. The energy released from this fission and fusion would be immense, equivalent to a large thermonuclear explosion. But unlike a bomb, this energy would be directed, focused downwards in a narrow beam into the planet.
So, for anyone on the surface, what would they experience? A massive explosion?
A massive and profoundly strange one. It wouldn't be a mushroom cloud expanding outwards, it would be a directed blast into the Earth, instantly creating a deep, glowing hot tunnel miles into the crust. The immediate seismic shockwave would register on every single seismograph on the planet. It would be an instantaneous global earthquake of magnitude 9 or 10, originating from an infinitesimally small point.
Okay, so it's already caused an unimaginable catastrophe on the surface, and it's just getting started. It's now plunging through the Earth's mantle.
And it's not slowing down in any meaningful way. Its momentum is far too great. But as it travels, something else is happening. It's accreting matter.
Accreting? You mean it's eating? It's growing?
In a sense, yes. The matter it vaporizes is pulled into its accretion disk before being consumed. This superheated matter is superheated to millions of degrees, releasing vast amounts of energy in the form of gamma rays, X-rays, and other high-energy particles. The black hole has effectively become a needle-thin thermonuclear engine tunneling through the very heart of the planet.
And what does that do to the inside of the Earth? That can't be good.
Not good is a colossal understatement. It's injecting an incredible amount of heat and kinetic energy directly into the mantle. It would catastrophically disrupt the slow-moving convection currents that drive our tectonic plates. Imagine dropping a sun-hot poker into a pot of thick, simmering soup.
Right, so you're talking about triggering volcanoes, earthquakes.
On a global and unprecedented scale. The models show that the energy injection would be more than enough to create new, supervolcano-like mantle plumes. These wouldn't surface immediately, but decades or perhaps centuries later, these plumes would reach the crust, leading to extinction-level flood basalt eruptions that could last for millennia.
My goodness, so the planet is already doomed, even before it gets to the center. What happens when it hits the core?
The core is even denser, primarily iron and nickel. The accretion rate would spike dramatically. The black hole would actually gain a small but measurable amount of mass as it passes through. The energy release would be at its absolute peak here. According to the simulations, the entire planet would vibrate. It would ring like a cosmic bell.
You mentioned your unbelievable findings earlier. Is this it? The long-term volcanic activity?
That's part of it. But the most shocking finding, the part that kept me awake at night, relates to the exit. The black hole has now tunneled through nearly 8,000 miles of rock and metal. It has absorbed matter and radiated unimaginable energy. The planet is fundamentally wounded, but the final act is the most violent.
So it's about to come out the other side, probably in the middle of an ocean somewhere if we're lucky. What does the exit wound look like?
It's even more violent than the entry. All that superheated, pressurized matter from the core and mantle that was being dragged along in its gravitational wake, it now has an escape route.
Oh no.
As the black hole exits, this jet of core material, a plasma hotter than the surface of the sun, follows it out. It erupts from the exit point like a planetary-scale blowtorch.
So you're telling me it's not just a hole. It's a volcano made of the Earth's liquid iron core erupting directly onto the surface?
Precisely. A volcano unlike anything we could ever conceive. It would blast a significant fraction of Earth's mass out into space, some of it reaching escape velocity. It would also create a new continent's worth of land from rapidly cooled core material. The atmospheric and climatic effects of this alone would be apocalyptic, triggering a global winter that could last for centuries.
Okay, that's already the end of civilization as we know it, but what about the long-term damage to the planet itself?
This is the truly unbelievable part of the model. The tunnel created by the black hole doesn't just collapse and fill in. The intense heat and pressure from its passage essentially sinters the rock, creating a new permanent structure inside the Earth, a hollow, glass-lined tube of super-dense, exotic matter.
A permanent scar running through the entire planet?
Yes, and this hollow tube would profoundly alter the fluid dynamics of the liquid outer core. My models show that it would disrupt the geodynamo, the convection process that generates Earth's magnetic field.
Our magnetic field? The thing that protects us from solar wind and cosmic radiation?
The very same, the shield that makes life on the surface possible. The field would become unstable. It might flicker, weaken, or even collapse entirely over the course of a few thousand years. Without it, the solar wind would begin to strip away our atmosphere, boiling our oceans into space. Slowly, inevitably, Earth would become another barren Mars.
So the initial impact is catastrophic, but the long-term effect is the complete and total end of all life.
That is what the mathematics and the models suggest. It's a slow, inevitable death for the entire planetary biosphere, all caused by a single atom-sized projectile that passed through in less than a minute.
Okay, Richard, after all of that, I need you to give me some good news. Please tell me this is purely a thought experiment. What are the actual chances of this happening?
The chances are, for all practical purposes, zero. The density of primordial black holes in the universe, if they exist at all, is thought to be incredibly low. The odds of one just happening to be on a direct collision course with a target as minuscule as Earth are astronomically, vanishingly small.
That is a genuine relief to hear, but it does bring up another question. All of this assumes the black hole is moving at a tremendous speed. What if it wasn't? What if a primordial black hole entered our solar system on a slower trajectory and was captured by Earth's gravity? What would that look like?
That's a fascinating and equally terrifying scenario, David. A capture scenario. It's something my colleagues and I have debated over coffee. The physics changes completely. Instead of a quick puncture, you have a slow, agonizing death. Don't tell me. The mathematics work if Planet 9 were a primordial black hole with roughly 5 times the mass of the Earth. It would explain why we can't see it, but we can detect its gravitational influence on other objects. It's a long shot, but we are actively looking for the kind of faint gamma-ray emissions from Hawking radiation that such an object would produce.
So these things might actually be out there, just hopefully very, very far away from us.
We certainly hope so. The universe is a vast and strange place, David. We've only just begun to scratch the surface of its secrets, and some of them are quite terrifying.
Well, Richard, you have successfully terrified me and blown my mind in equal measure today. A mountain mass bolide that could kill our planet slowly from the inside out? It's truly the stuff of nightmares, but also incredible science. Thank you for taking us through your findings.
The pleasure was all mine, David. It's why we run the models, to explore the very limits of what's possible.
That's all the time we have for today on What If. Join us next time when we ask another reality-bending question. Until then, stay curious.